All right, so hopefully those of you who are supposed to be in Friday's class going to find your way here today. Looks like we're down a few people, which gives me kind of time to mention I will have kind of that first online quiz posted after class today. One of the last questions on it, well, the last question on it will be whether or not you want to attend in-person classes for the rest of the semester. So, you know, seeing that there's already people kind of not here on what would literally be their first day, I'm guessing there's some people who are just planning on kind of watching these on Zoom. If that's, I've been even kind of, people have reached out where they're kind of commuting for a long time and if it's the only class. And so I understand that. But I'm going to ask you whether or not you want to attend in-person classes for the rest of the semester. That way, those of you who respond that you don't, I'll kind of move you off the in-person class list. I can whittle it down a little bit. So maybe we can get in here, you know, more than just once a week for those of you who want to be here. Okay. So that'll be the last question. There'll be some other questions like, you know, are you a freshman, sophomore, or junior? Just some kind of like somewhat demographic, like me getting to try to get to know who you guys are as a student. Not demographics and like age and things like that, but in terms of like student demographics. So we stopped kind of with these examples last class. Today we'll kind of jump into some material, start to talk about what the data that we're going to be dealing with looks like, some characteristics of it, and at the end I'll do a little bit of work in Excel, kind of initial work in Excel to kind of familiarize us with some of the terminology I'm going to be using when we use Excel. So actually, let's make sure, especially for the first few classes, okay. I'm always going to be paranoid that I didn't hit record, so I might check that sometime. So we already kind of went through these examples last class. Here's kind of a data set. I said I'll try to use sports data. If I do, I'll kind of tell you why it doesn't matter. Here I'm using the Chicago Cubs roster, only because after winning the World Series, finally I can actually admit to being a fan. But this could be any company, right? We've got a bunch of different players, their position on the team, and their salary. This could very well easily be, you know, I don't know, Mary Jones, who's an accountant and makes $50,000, you know, whatever it is, okay? So when we think about a data set, I'll start talking about things in terms of the rows, right, are going to be our observations. So each row represents a different kind of subject, right? So a different observation, right? For each one of those observations, we're then going to collect data on 3 different variables, okay? So the variables are going to be the columns, right? Here I'm collecting information on that person's position, but I've got 10 different observations I'm collecting that variable of position for, okay? So I've got player name and salary are kind of my other variables there, okay? Shouldn't be anything too crazy, right? So my rows are my observations, my columns are my variables, okay? So we're gonna have different types of data we can collect. So we'll talk about how we kind of define them and what they look like. So the first is gonna be qualitative, right? So this is gonna be anytime we have something that's essentially not a number, right? Anytime you're collecting information on a specific observation that's a characteristic, but it's not a number, it's some type of a name, right? So this could be like car colors, right? Let's say I have a used car dealership. I'm collecting colors of the cars on my lot, you know, red, blue, green, black, right? Those aren't numbers, right? The second is going to be quantitative, which essentially they are numerical, right? They are numbers, okay? So these are probably more what we're kind of familiar with in terms of variables. So this would be like I'm collecting like the mileage on these used cars. This would be if I'm collecting someone's salary. This would be if I'm collecting someone's height, you know. Whereas qualitative would be like if I'm collecting information on someone's eye color, right? Just a word, right? There's no number associated with it. So here's kind of our 2 types. And I know that, I feel like in grade school, or not grade school, maybe it was like middle, there's some kind of way you remember qualitative means words. The way I always remember it is that quantitative, like quantum physics, is a lot of math. So that's the numbers, right? That's, you know, maybe that's a stupid way to remember, but maybe that helps. So quantitative, right? This is going to be our numerical variables. Qualitative, this is going to be kind of our word variables. If you want to, you know, categorical, but words, right, instead of numbers. Okay. We can break it down a little bit further, right? So within each of these 2 categories, we have 2 different types. So Qualitative variables can be nominal, right? So a nominal variable is a word identifying characteristic that has no intrinsic value. So knowing the color of a car, I can't rank those cars. You know, maybe I could for my individual preference, but in terms of like their actual, you know, value, I can't really rank those cars based off of color. Okay? So I've got kind of another example, you know, if we collected hair color, right, as kind of, I was talking earlier about some individual level data we can collect, right? I can group people, all these people have the same color hair, but I can't like rank the different hair colors, right? I can't order the people based off the hair color. It doesn't really have any value to me. A lot of times, another nominal variable we'll collect is gender in these surveys. We'll see, you know, in the data set I showed you earlier, like the positions, starting pitcher, first baseman, shortstop, those were just words, right? They have no kind of value in terms of, we can't kind of order the players based off of those, okay? Any questions on this? Wouldn't be too bad, yeah. So yeah, we already had that kind of position, and even player name would have been a nominal variable in that data set we had earlier. Okay? So ordinal variables are a little bit more useful. When I say more useful in the sense that they actually do have some intrinsic value. So we are able to somewhat like order the observations, right? Order the ordinal, right? So some examples of this would be, you know, when you do these like teacher evaluations and they ask you a question, so this one is whether or not the instructor is effective. You can strongly disagree, neutral, agree, or strongly agree. Well, you know that everyone who strongly agreed thinks that this is a more effective teacher than people who disagreed, right? You know, you can rank the responses. Now, within people who answered strongly agree, I can't tell if one person strongly agreed more than another, right? But at least I know those who answered strongly agree thought this was a more effective teacher than even the people that said agree, okay? Education levels, whenever we ask somebody what their highest level of education or their highest degree received, really what we're doing there is we have words, right? I mean, high school, college, graduate degree, but I can rank the people based off of those responses in terms of I can tell you who has a higher level of education, right? Graduate's degree would be above the college, some college, high school, less than high school, okay? So these are some nice examples of ordinal variables. You know, another good one is letter grades. If I'm not able to actually observe what their percent was in the class, I can just see they got an A or they got a B. Well, I know that somebody got an A scored higher than someone who got a B, but if I see two A's, well, someone could have got 94, one could have got 98, I don't know, right? So it's useful, but it's not, you know, it has its limitations, okay? So nice ordinal variable, letter grade. So actually, let me see, I think we did this last class. So we'll go, before we talk about discrete, we'll just go put a new slide in here so I can, so if we want to think about what we just kind of did, what we said was we've got, I did not spell that right, where did I mess up? Qualitative. So I've got these qualitative variables, and then these two variables are qualitative, right? But they're a little bit different. So we had nominal variables, and then we had ordinal variables. So it's like under the umbrella of qualitative, we have two types of qualitative variables, one nominal, the other ordinal, okay? And I'll draw this out for you what we're about to do next too before we talk about them. So we've got quantitative variables, and in just a second, I'm going to break these down into two different types. One, which we're going to call discrete. And after we talk about it, this might make a little bit more sense, but I'll put kind of integers next to that. And then another type, which is continuous. Like I said, once we talk about them, it might make a little more sense why I'm putting this in here, but those are kind of, we think of as decimals. Okay. So these are our different kind of types of variables. We already talked about the difference between nominal and ordinal. So I'll give you guys a second, and then we'll kind of move on to talking about discrete and continuous. Still see people writing, so I don't want to. Okay, we're good with this? All right, so I'm going to clear this so we can keep moving. So discrete variables, they are quantitative, they are numbers now, right? So nominal and ordinal were words, now we've got numbers. So discrete, we'll talk about the examples, but the easiest way to think about this is a number line. I can see 1, I might be able to see 5, I can't see 7.592, right? So basically, there's gaps in between the numbers that we can see. And typically, not only are there gaps, but the number of numbers we can see is finite, right? There's a small number of values that we can actually see. Okay? So examples, if I ask someone the number of siblings they have, 0, 1, 2, 3, 4, right? We can't see 1.5 siblings, right? That'd be a bad thing. So, that's a good example where it's integer values. And discrete variables don't have to just be integers. So I was trying to think of a good example last class, but I don't know why this came to mind. But like Ziploc bags, like you don't go buy one Ziploc bag, right? Typically they're sold in quantities of 10 or 20. So if you were looking at like a purchase order from these companies, you're never going to see, 79 bags because they're sold in these usually 10 blocks of quantity. And so there maybe the discrete variable you could see 0, 10, 20, 30, 40, 50, right? You have those gaps, but it doesn't just have to be that you can see every integer. It could be that you only even see the tens, right? But usually more often the examples that we'll use here are kind of like the examples I have up here on the board, where there's really only going to be a very small subset of integers that you could see, right? 0 through like 10 or something like that. Continuous variables, we'll go right to the number line again. It's basically you can see 2, you can see 5, you can see 6.39129 right? Whatever value you can think of. Now, some examples of this might be things like height and weight. If we had a really good measuring tool, we could actually measure height and weight out to whatever decimal we wanted, right? There we might be somewhat constrained by the limitations of the devices we have to measure, but we can at least get this out to a decimal, right? Same thing with salary, right? You can see tons of different values for salary out to the second decimal. So for the sake of what we're doing in this class, I'm never going to try to trick you on an example. Anytime you have a variable where you can see a decimal response, think of it as continuous, okay? If you really wanted to be a stickler with me, and I had one student who, I think it was it might have been a longer class, and I think maybe we got to this day 1, and they really tried to pick a fight with me. But they told me I was wrong, that salary isn't continuous. And I said, yeah, if we want to be theoretically down to the letter of the law, why would salary not be continuous? What's the very first thing you could get paid? Well, $0. What's the very next denomination of money you could get paid in? 1 penny. You can't get half a penny, so technically it's discrete, right? I mean, if you really wanted to be, but for the sake of what we're doing, these discrete data, the reason why we treat them differently than continuous is because it's not just that we see the integer values, it's a finite set, right? Here with salary, it's really not finite. I mean, we don't know where it ends every year. Someone's getting paid a higher salary than the year before. I look at it, we got Jeff Bezos and Elon Musk, so I mean, really anything with a decimal, we're going to treat as continuous. And honestly, once we get to talking about things like samples, even if it's not truly continuous, we generally have large enough sample sizes where it doesn't matter. All right. So, if we think about salary here, I think I censored it just to make it easier to see. But these all had decimals associated with them, so we can think of salary as being our continuous variable from that original data set. Okay. I'll go through this a little bit quicker because it's not overly important, and I'm not going to necessarily quiz you on it. I just want to make you aware of the differences. So we've got 3 different types of data sets that we can see. So one is cross-sectional. So this is where we have multiple subjects at one point in time. So this would be like if I collected what your current GPA was from every single person in this class, right? Multiple subjects, but right now, this one point in time, I'm collecting that's when I have your GPA. Not your GPA 2 years ago, your GPA today, right? Time series would be if I took one subject, so maybe I single one of you out, and then I collect what your GPA was for the last however many semesters you've been at Ball State, right? Each semester I have your GPA, so multiple points in time, but one subject, okay? Panel data is if I just mash the 2 together. So that would be like if I had every single person in this class, and I had what your GPA was, each of you at each semester, right? Multiple points in time, multiple subjects, okay? So, I'm never going to ask you necessarily to identify these like on an exam or anything like that, but when we start looking at these data sets, these are the three types we'll be seeing. Another examples of these, cross-sectional. Let's say I had every country in 2011, so multiple subjects, one point in time, and I collected their GDP. Right? Now, just because we're doing cross-sectional where it's one point in time, I can collect information on multiple variables, right? Here I've got, what, 1, 2, 3 variables, technically 4 if you count country name, right? So you can collect multiple variables at one point in time on these multiple subjects. That's fine. It's just that you're collecting, GDP and education expenditures in the same time period, in the same year. Okay. Time series. Got an example here where I took the US and grabbed the unemployment rate for about a 10-year time period, right? So multiple points in time, one subject, right? And that would be a good example of time series. Now, we won't get to it today. I doubt it. Monday, I think we should. We'll start to think about how what we use time series for. We can make some really nice graphs out of it. So we'll look at that. And then panel data was where we kind of mashed the two together. So here is a fun little, I always like to just let people know I had it because I think maybe some of you are aging out of it now, but I had every student who took the I-STEP score between 2009 and 2011, and we're in grades 5 through 8. So I've got all these different students. They're just identified with a number, not a name. But like here's student 1, 2, 3, multiple years for each student, and kind of what their I-STEP scores were. Okay. All right. Do a quick discussion here about population and samples. This will kind of pop up again later or different points in the semester. But just thinking about when we look at a data set, if we had a population data set, that would be if we had every single person that belonged to the group we're interested in. So this is like, if I want the average income in the US, this would literally be, I'd have to get a population data set, I have to have every single person's income in the US, right? So that's, you can imagine, it's hard to get population data sometimes, right? Especially if you're interested in large groups. If I'm only interested in something like econ majors at Ball State, maybe it's a little bit more attainable to get population data on something like that. But when I'm talking about something like the whole US or the entire world, well, population data sets seem pretty out of reach. Okay? So because of that, and I think I said here, we've got the census, which attempts to get population data. You don't have to worry too much about that. But that is typically what we use to get population data on people in the US. But because it's unattainable most of the time to get population data, we're stuck with a sample, right? So hopefully, and we'll talk later on in this course about the biases that could exist and how we get a good sample, right, an unbiased sample. But usually we randomly sample and we end up with this kind of small subset of the population or the small sample of the population, okay? Does anyone else hear that? Okay, I was making sure it wasn't just me. Hopefully that goes, I think it went away. So, the sample is going to be quite a bit smaller in the population, but it's obtainable. Right? So, why do we need to have the sample? I kind of already mentioned. I mean, I'm going to close the door. I don't know if that'll help. That's what it is. a little irritated. What was I saying? Oh, to obtain population data, it could just be really expensive. I mean, if we're doing door-to-door stuff or anything like that, you can imagine it starts to add up pretty quick. Sometimes, like let's say I was concerned with obesity in America and I go around and I try to record biometrics on people, so I'm getting their weight, their muscle mass, I don't know, all the other things I need to measure that. Well, especially if I'm just taking their weight, by the time I collect every single person's weight in the US, what do you think's probably happened to some of their weights? One up or down, right? Especially if there's like a month-long period, right? By the time I actually collect the data, it's no longer even valid data. So sometimes it's just not even feasible, right? It's just impractical. And so we kind of have to settle for just a smaller sample, right? So I'll come back to this in a second. But so using that sample, we make generalizations about the population. That's what we'll kind of refer to as statistical inference, right? So I can't get population data, but I can start to compute statistics from the sample. And if I've done a good job of randomizing the sample, I'm pretty, whatever I find from the sample should match the population pretty well, okay? So that process is statistical inference. Descriptive statistics is really just some of these statistics we're going to use to describe the data. I mean, it's, it's literally almost what the definition is, but this is an overly important term, but I might throw that out there when we're thinking about measures of central tendency and dispersion that we talk about next week. Okay. We already have, I duplicated this slide and I never deleted it after I realized this. So here's the slide again. So now what we're going to go to is, okay, we understand the different types of data, qualitative, quantitative. We're going to focus today on maybe the beginning of Monday on qualitative variables and how we come up with some nice graphs that tell us something very quickly about that variable, or the responses to that variable, I should say. So let's say I have this data set of people. I think 10 people, if I'm looking at this right. They're letter grade, and I want to give a quick frequency distribution of them. Right? So what a frequency distribution does is it looks at every single possible response that you could see for a variable. Right? Once you look at every possible response you could see for a variable, you count up the number of observations that were that specific response. So if I think about here, I say, okay, the first response I could see is A. How many A's are there? 1, 2. Write that frequency or that count down. The number of B's, that's the next possible response I could see. 1, 2, 3. 3 B's. I then go through every single possible response and count the number of observations that are in that category. Now I have my frequency distribution. Okay? Now it's pretty easy to do by hand with a small data set, right? What we'll do by the end of class is I'll show you how you would do this with a larger data set in Excel. Because if I had like a 2,000 person data set here, I don't want to do this by hand. In fact, I did this, maybe I'll pull the file into class. I did this at one point with every student who had ever taken my class, or my stats class, and looked at what my frequency distribution was across like all of them. It was a pretty big data set, right? So it wasn't something I was going to do by hand. So we'll hopefully today we'll get an idea about how we can do this in Excel. So once I have this frequency distribution, now it tells me pretty quickly, I can identify, oh, this is the most common grade, here's the next most common grades, and then not a lot of people getting kind of D's and F's, right? So, we could do this with a larger data set as well, but here's kind of a nice, easy way to first start thinking about it. Now, it's fine with a small data set. I can kind of see the relative size a little bit easier. But once these numbers start getting larger, once I have more possible responses here, if this wasn't for a letter grade, maybe it was for like, we go back and using the car colors example. I've got more than just 5 colors. It might be hard to kind of see, okay, well, I know this is the most common, but what are, the next most common? Is there a quick drop off? So a lot of the times we don't just want these frequency distributions, we're going to want relative frequencies. So relative frequencies tell us the proportion of the data set that was this specific answer for that variable, or that specific observation, that specific like label for that variable. Sorry, I was blanking on the word. Now, if we think about proportions, right? We want to think about what's the highest proportion that we could see. Well, if every single, let's say we had 100 students and they all get A's. So 100 divided by 100, 100 out of 100 students get A's, that's a proportion of 1. So that's the highest we can ever see it for a proportion. What if 0 students got A's? Well, 0 divided by 100 is 0. So the lowest we can ever see is 0, highest we can ever see is 1 for proportion. But what if 50 of 100 students got an A? We would say 50 out of 100, 50 divided by 100, or a proportion of 0.5, okay? So these proportions are always going to be between 0 and 1. They're always going to be decimals, right? The way that we turn those frequencies into proportions or into these relative frequencies is we simply divide by the total number of observations. And an example I was just kind of saying out loud was out of 100 students, right? But it's really, I was using that 100 students as my total number of observations. If we go back here, the number of students who got A's, well, there's what, 10 students, 2 of them got A's, so the relative frequency here would be 2 out of 10 or 0.2. So that's all we're doing with the relative frequencies. We're taking the frequency for each category, dividing it by the total number of observations, okay? Any questions on that? Okay with that? All right, let me check here, all right. So let's say I had that old data set with Cubs roster data. And I looked at it and I said, well, where's the majority of my team? Like, what position do they play, right? So I went through every single possible position, and I counted up the number of players in the roster who were in that position, right? So that's my frequency distribution. Well, I can quite clearly see that the most common position is pitcher on a roster, but like what proportion of the overall kind of roster is that made up of? How high is that relative to the other categories? I'm going to turn these into relative frequencies. So all I do here, I added up my frequencies. So when I add up my frequencies, if I've looked at every possible response that I could see for that variable, every observation should be counted one time, right? It only should belong to one of these categories. But if I've done my frequency distribution correct, I've counted every single observation at least once, right? So when I add up these frequencies, it should just be counting every single observation once. So when they add them up, that would be my total number of observations. So here, when I add up these frequencies, I get the total number of observations, which is a 25-man roster, right? And in Major League Baseball, okay? So it kind of checks out. So I'm going to divide each one of these frequencies by that total number of observations, 25. And if I do it for this first one, you can kind of see 13 over 25 is 0.52. But then I would just go through and do that for every single other response, right? And so I can kind of see, right, the relative frequency of being a pitcher, if I selected one player at random off the roster, much higher relative frequency for that position of pitcher than any of the other positions, okay? Any questions on this before we keep moving? What should these relative frequencies add up to? Yeah. Close. Yeah, so the numerator, right, if you add up the frequencies, that'll be your total number of observations. Remember, with the relative frequencies, we divided every single number by the total number of observations. So total number of observations divided by the total number of observations. I just feel like I slurred that together. All right, anything divided by itself is 1, okay? So anytime you get to this step, if you have the relative frequencies for every single possible response, if they add up to anything other than 1, you know you made a mistake somewhere. You got to go back and figure out where that's at, okay? So this, we're at a point where I said these relative frequencies, right? We can think of them as proportions, right? They're going to be between 0 and 1. They're going to be decimals, right? We don't talk in proportions very often, but we talk a lot in percentages, right? So we might want to do percent frequencies as well. Well, if I've got my relative frequencies, let's say we have that example where 50 of 100 students get an A. Well, that'd be a relative frequency or a proportion of 0.5, but 50 out of 100 would be what percent of the students get A's? 50 out of 100, 50%. So what's the difference there? Well, the relative frequency of the proportion was 0.5. The percentage is 50. I moved the decimal 2 places, or I multiplied by 100, right? So all I need to do to get a percent frequency is take that relative frequency, right? That's what this represents, and multiply it by 100. Okay? Pretty simple. But you know, we'll run into this problem, not a lot, but excuse me, a little bit throughout the semester, because we do say things like, well, yeah, 50% of the class was late. We don't say, yeah, a proportion of 0.5 of the students were late. Like, you just don't talk like that, right? So a lot of the times we'll be dealing with proportions, and I know, at least for me, my brain automatically, like, when I first see something, like if I hear 50 out of 100, my brain goes to 50%. It doesn't go to the proportion of 0.5 first. I can figure out that's what it is, but my brain goes to the percentage first. So a lot of things that we'll be dealing with proportions or relative frequencies, but really to move them to percent, all we're doing is multiplying by 100 there. Okay? So let's say I have this example where I've got, 7, 8 years of data, and I've got the causes of death. So I had all the death records. I went through and found the total number. You can actually do this on the CDC. That's how I came up with this. You can see the total number of deaths that come from heart disease, total number of deaths that come from malignant neoplasm, which is my understanding is essentially cancer, so on and so forth, right? So I've got my frequency distribution. If I add up, because I have this other causes catch-all category, if I add up all these deaths, that should just be the total number of deaths that I have or my total number of observations. So I went through, added up these deaths, and I get about 16.6 million people died over this time period. Right? So how do I get my percent frequency for malignant neoplasms here? Easy as that, right? Take that category's frequency, so 4.4 million, divide by the total number of observations, 16.6 million, about 4 out of 6, that's about 0.25, if I'm really roughly, rounding there. And then I have to multiply by 100, so about 25%. Now that's not exact because I rounded these very egregiously. But if I take the exact numbers, right, 4.4 out of 16.6, it's about 26.8%. Now, before I had done this calculation, before I dove into the formula, and this is something that we have to remember throughout the course, right? If I have multiple choice and I have some answers in front of me, sometimes I'll do this because I want you to be able to narrow it down. Occasionally, I've even done it where you can identify that only one of the answers even makes sense by just thinking about fundamentally what you're looking for, right? What the statistic you're looking for tells you. So here we're looking for the percent of deaths that come from malignant neoplasms. Well, if 4.4 out of 16.6 million people are dying, I mean, I don't expect you to be a math whiz, but 4 out of 16 million should tell you that's a pretty good, like, it's not insignificant, right? It's not 1% of all deaths. Well, 0.27 and 3.7% seem way too low, just thinking about that 4 out of the 16 million deaths are coming from malignant neoplasms, right? So right away, ruling out B and C should be pretty easy to do. From there, yeah, when I really rounded a lot, I got 25% and A was closest, but I rounded a lot, so maybe it was a little bit high. At least D is in the ballpark, right? B and C doesn't even make sense for what we're trying to find, okay? But then, of course, when we use the actual equation and formula, plug our numbers in, we can get the exact, we don't have to just throw darts at it. But, I think sometimes before you even work through it, just thinking about which of these 4 answers even remotely makes sense can really help you, mostly help you from making really simple errors, right? Okay. Oh, so one thing I wanted to mention here. So I have, let's say I did this for every category. Just like the relative frequencies add up to 1, the percent frequency should add up to 100%. So if you add up your percent frequencies and you don't get 100, you made a mistake somewhere. Okay? Questions on that? Shouldn't be too bad. So usually this would be like we might work through something like this, like a sample question. Usually that's what I'll have it titled as. Typically, not today's quiz, but in moving forward, the sample questions, I'll usually use those to kind of come up with some of the online quiz questions. So if you go to those online quiz to find something that would be similar, look through that day's kind of lecture slides at the sample questions we worked through, and that should kind of help you with those online quiz questions. Okay, so we'll kind of skip this stuff for now. We might come back to this on Monday, but what I want to do now is do some Excel, okay? So, like I said, I'm going to start off assuming you guys know jack all about Excel, right? So, we call this whole thing, when I open a new file, it's called a workbook. I'm not going to quiz you on these names. I'm just trying to give us, kind of get us into this. Down here are worksheets. So if you open a new one, you only have one sheet, but you can add multiple worksheets to your workbook, right? So you kind of keep everything in the same thing. The other, well, oh, never mind. I won't go that. We'll save that for another Excel. I don't want to get too much too soon. So each one of these cells in a worksheet is referenced by the column and row, right? So this cell that I've selected is cell C7, right? This cell is I8, right? So each cell has a reference. So let's say I put this value of 100 up here in cell A. So just type the number in, hit enter. If I want another cell to use that value, I can start out with an equal sign. So this tells Excel that I want to do some kind of math, or I want to use a cell reference, or I want to use one of your built-in functions. Okay? So we could do math here. Like I could take 100 and divide it by 50. Right? Excel will do that math for me. So I honestly, when I'm working through things for this class, I typically use Excel as my calculator instead of even using an actual calculator, pulling up an app on my phone or something. I'll just use Excel because it'll do all the math for you. Now, what if, right, I was trying to divide that original number by 50, but what if the original number changes? Okay, so let's say instead of 100, now this becomes 50. well, then I'd have to go back in, I'd have to change this one, and anywhere else I use at 100, I have to change it. Right? But if instead of the actual value, I use the cell reference, okay? So I reference that cell, and I don't have to type in A1, I can just click on the cell, right? So I want to divide whatever number's in this cell by 50, okay? Well, now it doesn't matter what this is. When I change this, oops, now anywhere where I reference that cell, it updates to the new value, right? So you can imagine, if I have like, I know, what would it be like? If you're trying to sell health insurance, not health insurance, like life insurance or like whole term life policies, or you're trying to like give somebody a projection about what their loan payment will be based off of certain interest, and that interest could change over time, or that interest might be different for different people depending on their kind of risk. You can just have this whole thing worked out, but yet if that interest rate changes, if you just reference that cell, you can go back and change one cell, and the whole rest of your projections will automatically update. Okay. So some of the things that we'll do throughout the semester, I'll show you the real power of using these cell references and how much work it can actually save you. But I'll show you a quick little one right here now. So let's say I have these different values, and I want to know what the original base plus these values would be. So in this cell, I want to take 150, add 10. In this cell, I want to take 150, add 20. In this cell, I want to take 150, add 30. You know, you kind of get the idea. Well, if I tell Excel this equal sign, so okay, take 150 and add to it this value. I'm not going to type the value of 10 in, because anytime I use a cell reference, if I copy that cell down, it updates the reference by however far I move it. So if I go down one row, C1 becomes C2. And if I go down 2 rows, C1 becomes C3. If I go over one column, C1 would become D1, right? So it updates those references by however much I'm moving them, okay? Well, that kind of helps me out, because if I copy this down, you know, I want to take in the next cell 150 plus 20, so instead of C1, it would be D1. Okay, so it'd be using that new value of 20. So I copy this down, I think all is going to be great. Something looks weird here, that's not 150 plus 20. Oh, because when I reference this original value, that cell reference will update as well. And I don't want that one to change, right? I want to keep using the value in A1. So I go back, I can delete these. I go back, I say, okay, well, I want this cell reference to change when I copy it down, right? But I don't want this one to. So how can I do that in Excel? If I put a $sign in front of the column and the row heading, it freezes that cell reference, right? So it stops it from updating when I copy it. So now when I go down here, now it's still using 150 from cell A1, and it's updated this to now adding 20 instead of 10, okay? So you can imagine, like I've seen people do these sheets. I've done a couple of them on my own. But like if you're trying to come up with like what the yearly payout is of a certain investment, depending on like your principal and all this other stuff, well, I can enter something into one cell, and then I just got like every other following year, I can copy that down through a process similar to this, right? So there's a lot of real world application to like this very simple little example that we just did, right? There's a lot of times where you see just this process, you do something similar, right? Where you freeze that principal cell, that original value, and then allow what you're adding to change kind of using this additional column. Okay? Any other questions on that? Okay, so go to this new sheet, make sure we can all see it, and we're gonna see what would happen if we had, oh, what am I doing? Color, black, red, blue, black, yellow, green, blue, red, black, okay. We have like few cars here. Well, I'll add a few more. So green. All right. So we've got a bunch of different cars. You can imagine this data set could be much larger. If we have enough time at the end, I'll show you kind of some of these tricks do work with large data sets. So I've got all these different car colors. So I'm going to put down every different possible car color that I had in this data set. And I think I got them all. Okay. So I want to come up with a frequency distribution for the car colors here. Okay. So what I'm going to do, I could go through and count this by hand, but if I had like 2,000 cars here, that's not possible, right? I can't go through 2,000 and count the number of red. I mean, I guess I could, but it's not going to be fun, right? So another thing that we can do with this equal sign is tell Excel to use a built-in formula. So this is like a pre-coded formula into Excel, and just like any function, so I'm going to show this to you. Just like any other function, right? If I had y as a function of x, every function, you need to tell it what the value of x is, right? Well, here, right, the function is COUNTIF, and it has two things it wants to tell you. It has like two x's, essentially. First, tell it the range, then put a comma, and then tell it the criteria. So what the COUNTIF does is it goes through a range of data, and it counts the number of observations that meet a certain criteria. So I might say, look, go through this data and count the observation if it says red, right? So the first thing I'll do is select the range of data. All I do to do that, click on the first cell, left click, drag down with my mouse, select the entire data set, right? Every single observation. Now a nice shortcut for this, right? If I hold Control Shift or Command Shift on a Mac, then the down arrow, it goes all the way automatically to the very last observation. Doesn't help me out a whole lot with a small data set like this, but if I got 2,000 observations, instead of dragging down with my mouse, that Control Shift or Command Shift on a Mac down arrow shortcut helps a lot, okay? Saves a whole lot of time. And I gotta move this guy out of the way. I don't know why it moved over there. So if we told it the range of data, comma, the next thing it needs is what am I trying to see if it's true? Well, I wanna see if this color is red, or is it equal to red, okay? So just the syntax of the COUNTIF formula, and eventually what we'll use is the COUNTIFs, okay? You have to put quotation marks around if you want the equality or if you want it to be greater than, less than. The greater than, less than doesn't really make a lot of sense with qualitative variables, but the equality sign we will be using, right? Is it equal to this phrase red, okay? The next thing, we need to put an and sign, okay? This is just good convention. There are some rules and ways where in the COUNTIF function you don't need the and sign, but I'll mention one in a second why we would need it, and just to default to get used to using it. It'll always work if we put the and sign after this equality, so let's just get used to doing it that way. So the next thing we're gonna say, is it equal to this word red? And because it's a text, it's a character, we have to put quotation marks around the word red, okay? So if I hit enter here, it should go through and say, how many red cars are there? 1, 2 red cars. So it should return to me the value of 2. Sure enough, it does. Okay. Now, what I could have done is instead of typing the word red in here, we already have red over in this cell. So I'm just going to click on that cell and use that cell reference. Now, the reason why I put the and sign in there is because it doesn't recognize that cell reference if you don't use the and sign. So you can not use the and sign when you actually put numbers or strings in there, but it's just good convention to get used to putting it in there, because otherwise you'll forget it's supposed to be there when you need to use the cell reference, and you know, it'll. Nope, if you use a cell reference, because it's already in this cell, is treating it as text. So when you put it in quotations, it tells Excel this is text, but because you're using a cell reference where it's already identified as text, you don't need the quotation marks around it. That's a good question. All right, so that will give me, I gotta show you that, that'll give me the same 2, right? Still counts those 2 red cars. Now using this function, I don't wanna have to type this in another 4 times. So I wanna try to copy this down, because I know if I copy it down, instead of using the color red, the next cell will count it if the color is blue, right? Because C2, if I go down 1 row, becomes C3, and it'll use the new color. So that'd be cool, because I can copy this down and get the number of blue, yellow, black, green cars really quickly. But what's one thing that I need to make sure I do before I copy this down? Yeah, this cell reference will update, but so will this cell reference. So I'll show you what happens. By the time we get down to here, what's skipping the first 4 observations in my data set, right? I'm not even looking through the whole data set now. So I don't want that reference for where the data's at. I don't want this to ever change. So I'll highlight it before I put $signs in front of every row and column. So a nice little shortcut is on a Mac, you hold Command T. On a computer, you hit F4, or if you have an FN key, which I do on this laptop, you hold FN and then hit F4. And it automatically puts the $signs in there for you. Okay? And then this kind of helps make it a little bit quicker. Sometimes if we want to freeze like a lot of things within it, then this really helps out. So now when we copy this down, the range of data should stay the same, but the color, the cell reference will kind of update, so we'll be using a new color. Sure enough, why is it not counting this green? Hold on. Oh, did I put a space? That's why I put a space after the word green. So, one thing that should be true, right, is if we were to add up my frequencies, I should get the total number of observations here. So if I look here, the total number of observations, so the first one is the word car color, so I've got 13. So if I wanted to add these up real quick, we have this sum function in Excel. So I could put equals sum and then just select the numbers I want to add up. Right? So I've selected all these numbers that I want to add up. I hit enter. I got 12. So what am I? Oh, I probably put a space on that one too, didn't I? I don't know why I did that on both the greens, but so you can see dealing with qualitative variables because of things like spaces. There's actually a lot of other programs that are better than Excel. But as long as you have kind of the normal convention, it should work pretty well. So now I've got all 13 observations there. Okay. How much time we got? 3 minutes. What else do I want to do to end class? I forget exactly where we got in the other class. Well, let's do one more thing. So if I wanted to do relative frequencies here, how would I turn these into relative frequencies? So relative frequency was just taking the frequency for that category and dividing it by the total number of observations, right? So I'll take this frequency, I'll divide it by the total number of observations. Now when I copy this down, I want to get the relative frequency for blue. I want this cell reference to update, right? Instead of using the frequency for red, D2, I want it to update, go down to D3, so we'll be using the frequency for blue there. But I don't want that total number of observations cell to change, right? I want to keep dividing by that total number of observations. So I'm going to freeze that cell. Now when I copy this down, it'll always be dividing by the total number of observations, but it'll keep updating to use the new colors kind of frequency. So copy this down, and I get my relative frequencies for each one of these different colors. Okay? If I use that sum function, right, that just adds numbers up for me in Excel, and I sum up all the relative frequencies, what number should this return to me? Yeah, someone holding up 1, right? Sure enough, we got all of them. Okay? So we talked about doing this by hand. We can kind of see how you can do this in Excel. I got 13 cars here. You can imagine how much more useful this is if I have 2,000 cars. Right? It saves me a lot of time. Gives me a quick glimpse into the data where most of my cars are blue and black. Yellow cars are pretty uncommon. I can quickly just see that. Okay? All right. So we'll keep working on some stuff in Excel on Monday. Eventually, once we're doing a little bit more in Excel on Monday, I'll post the kind of completed version of what we worked on in class because I just kind of started from a scratch file. Make sure that you get that online quiz answer because the last question is whether or not you want to attend in-person classes. Try to get on, answer that as quickly as you can. Today would be preferable, but it's not due till we start class on Monday. Okay. Also, what else is due before we start class on Monday? First Learn Smart assignment, right? Get on, get that code. If you have any issues or problems with that, please email me as soon as possible and we can kind of get that worked out. Otherwise, have a fun, safe weekend, and I'll see you guys again at the latest on Friday, and then some of you on Zoom. Hopefully, I'll see you guys here on Monday, okay? And I always leave Zoom open for a couple minutes afterwards, so if you have any questions as kind of people are heading out, you can ask those via Zoom as well. All right, have a good weekend.